of NP-completeness, and maybe, the subtext is, what the heck does P versus NP mean? And I think by now it's popular enough that most of you have probably heard this phrase or this term, P versus NP, but you might not have seen it defined properly anywhere. A formal definition of it takes some effort, and you have to go a bit into the theory of automata to define it, but there is a way in which one can explain it without getting into a lot of it, especially because in this course you've seen many, many examples of discrete optimization problems and like how to solve them using these techniques like greedy or dynamic programming or like shortest paths and all of these things. And so the place where really I think it makes sense to start, and by the way, if you might have seen this defined in terms of non-deterministic Turing machines, and all of these definitions are equivalent, but the most meaningful that I think is really in discrete optimization problems. So if you remember, in your typical discrete optimization problem, what you had was this sort of maximization, or it could be a minimization of some S, and typically S was, some subset of all options. So this was like some universe. This is some universe. It might be a maximization, it could be a minimization. So let me draw out a few examples. So for example, the simplest one is just shortest paths. And so in shortest paths, what is the set? This is like a path. And the universe is the set of all paths. Right? So one way to think of it is I give you a graph. I have two vertices. Say, find what is the shortest path. You're trying to minimize f of s, where f is the weight of the path. S denotes the path. Right? You can think of it like as a list. It's a list or a set, whatever. It doesn't matter. Okay? And there are potentially many, many possible paths. We did minimum spanning trees. So in minimum spanning trees, this is essentially a spanning tree. Right? And the universe could be like, sets of spanning trees, or even more simply, it's just a set of edges. It's some set of edges. We saw something like, Huffman coding, where now your S is your is a prefix-free encoding. If you remember, there was also like the optimal parentheses for matrix multiplication. So this was that scenario where you had M1, M2, M3, M4, and you're like, should you multiply it this way or some other way? Right, so on and so forth. And so here S is a parentheses string. Right, so you have all of these examples. Like if you actually step back and look at pretty much every single problem we've done, over maybe the past 4 or 5 weeks, it's all about examples where you're doing some optimization over some discrete set. And in all of these situations, what you have is, given S, f of s is easy to compute and there are exponentially many options for S, so minimizing or maximizing is not obvious. And so typically when I mean easy, I usually mean polynomial time. And when I say many, which of course I've explained over here, I mean exponentially many. So this is like saying it's like 2 to the n, 2 to the n square, n factorial, things like that. And this is saying it's n, n square, n cube, n to the fourth, n log n, whatever, things like that. Okay? So you would have this paradigm, and this happens in lots and lots of problems, where given a potential solution, it's easy to compute the value of that potential solution. It's like if I gave you a potential path from S to T, it's easy to compute the weight. Just sum up the weights along it. If I gave you a particular parenthesization, you can just compute, okay, this multiplication takes so much, this one takes next, so on and so forth. Or if I gave you a minimum spanning tree, you can check, yes, this forms a spanning tree and compute the weight. The problem is that there are many possible options, exponentially many options for solutions, and this is where a lot of the algorithmic work comes in, into figuring out how you find the optimum without looking over all possible solutions. Okay? Clear? Even at the extent of thinking of sorting in this paradigm, which is sorting is like optimizing over all permutations, and there's only one permutation that's correct. Right? So you can think of the value of a permutation is the number of mistakes that it has, number of things out of order, and you want to optimize over all possible permutations, which is an exponentially large set. But given a permutation, if I say, is this a sorted order, that's easy to check. You can just go through it and check if it's a sorted order. Okay? So there's a large class of problems, and dare I say, like pretty much every single problem that you've seen in an algorithms course or in a computer course so far usually will fall in this paradigm in some way or the other. Okay? Okay, so now so you'll see that, and this question, okay, so who was the first to ask this question? So there was Krakenbrot in the 50s. There was Gödel, I think, in 44. So what's interesting is, this is just at the period of the Cold War, or when the Cold War was starting. And so there were lots of Soviet mathematicians who were studying pretty much the same topic. And it's only like over the past 20 years that people discovered that, they've been doing the same things. And about maybe 20, 25 years ago, there was a letter of Gödel discovered in he wrote this in 1944. The letter was missing. Then someone found the letter, and he actually had asked this question. And the question essentially is this, can this optimization always be done efficiently? So what is the optimization? So it's like finding the shortest path, finding the minimum spanning tree, finding the best prefix encoding, finding this, so on and so forth. So for each example, we came up with a different algorithm. And what they were asking is there a generic procedure that can always optimize? Okay. So specifically, this function fs is easy to compute. In all of the situations that we care about, this is easy to compute. Versus f of s is easy. By easy, I just mean polynomial time to optimize. So in each of these cases, we proved that f of s is easy to optimize. Again, easy doesn't mean it was easy to come up with. Easy just means it was polynomial time. So easy, instead of easy, I will say efficient. So let's get rid of the word easy and say efficient. Okay? So in all of these cases, so in every discrete optimization problem, f is efficient to compute. And in multiple cases, we showed that f is efficient to optimize. And the question they were asking was, does this imply that? That if you had a discrete optimization problem where it's efficient to compute, can you always optimize? And somehow that doesn't seem like it should be true. Just because something is, yeah?
Does it go the other way where if f of s is easy to optimize for, f of s is efficient?
So usually if you're optimizing, then you can often compute it as well. But in all of our situations, you should really think of, we're assuming that the problem has this feature, that it is easy to compute, that it is efficient to compute, and we're asking, is it efficient to optimize? Okay, this is really where Trachenbroth's question started. Because he was studying about solving various problems and recognized that there were some problems where he got stuck and some problems that he could solve. And trying to understand why is it that some of them could be solved and some couldn't. Gödel was asking this from a different perspective. I'll just say this, I won't write too much about it. But he was thinking more in terms of like logic. So, for example, he was saying a proof is easy to check if it's correct. But does the fact that a proof is easy to check means that you can come up with it? The optimization is like coming up with the proof. And he said there seems to be something fundamentally different between checking if a proof is correct and coming up with the right proof. And it seems like there's something fundamentally different about being able to compute the value of a path to actually finding which path is the shortest. Right? It seems like the second task is much harder than the first one. But is it always the case? Like, what's going on here? So they were trying to formulate this question because they were getting stuck in certain problems and making progress in others. Okay? So let me try to formalize this a little bit more, because then I can tell you exactly what the P versus NP question is. And so I should say, like, while Trachenbroth was probably involved more in the optimization question, Gödel's questions were more philosophical. Or it was more mathematical in terms of, does it mean just because you can check that a proof is correct? So actually like you can write proof in a programming language, in a specific kind of language, and you have proof checkers, which will check that the proof is correct. So we know that proof checkers exist. But does existence of proof checkers mean that we can come up with methods that will actually find proofs? So he's asking, like, is there a machine that you could give it a mathematical statement and it would actually find a proof efficiently? That's what he was asking. So I'm going to convert the optimization to what I'll call a decision problem, which is sort of easier to think about. So instead of minimize, I'll just do minimization instead of maximization. Though again, they're all the same. Minimize S of f of s. This is optimization. Let us answer, given a bound T, is the min of S, f of s, less than T. So this is called a decision problem. And this is easier to think about. So the answer here is just yes or no. So it's like saying that in shortest paths, instead of asking what is the shortest path, they'll say, is the shortest path have weight less than 50? Or does the minimum spanning tree have weight less than 100? Okay? So okay, and the thing is that given a procedure that answers the decision question, one can come up with an efficient optimizer. Yeah, I should say efficient. So why is that? So suppose the shortest path, I'm not asking you to compute the shortest path, just the weight of the shortest path. Okay? If I could somehow figure out a way of just doing this, how could I use that to actually solve the optimization problem? Yeah? Okay, more specifically, how would I do it efficiently? Yeah, basically you have to iterate, but what is the best way of iterating? Since we've talked about repeated squaring and logs, like doubling binary search, some kind of binary search, right? You could say, oh, I know what the shortest path is. Is it less than 1? No. Is it less than 2? No. Is it less than 4? No. Just keep doubling, right? So you can do some kind of iteration, doubling or binary search by doubling or binary search. So what this means is efficient decision making. The decision is kind of equivalent to efficient optimizing. And it's going to be easier to think about decision making. Okay? So it's just saying, all I'm saying is that we're trying to understand optimization versus computing, but instead of optimization, I'm going to talk about decision instead. Because it's basically the same thing. Because if you can decide, you can optimize, and if you can optimize, you can decide. Obviously, if you can optimize, then this is easy. You just compute the optimum and check. Right? But also, if you can do the decision version, you can optimize just by this doubling trick. Okay? Okay. Okay, so now I'm going to come to this is sort of the heart of the matter. So again, let's go back to this graph problem, and let's just, in our mind let's have MSTs in our head. MSTs, but you could also do it with shortest path. So you want to do this sort of, so f of s, this is the MST problem. And so you want to check, is this less than t? Okay? So what they observed was that if the min of fs is less than t, if the answer is yes, then there is a simple certificate that is efficiently verifiable. Okay, so it's a lot of words here, but what am I trying to say? So I'm saying, suppose the minimum spanning tree is actually less than t. And I wanted to convince you that the minimum spanning tree is less than T. The easiest way to do that was I could give you a spanning tree, and you could just compute the weight. You could check it's a spanning tree and compute the weight and check that it's less than T. So in all of these problems, there is a certificate that is easy to check when you make a decision. Okay, specifically, what this is saying is, it's useful to think of this as an interaction between two people. So this is some polynomial time procedure. And this is sometimes thought of as an all-powerful oracle. It's interesting. People used to think of this as some weird game, and now with LLMs, we're actually, like, some people are treating the LLMs as an all-powerful oracle. So this sort of way of thinking is coming in. So suppose you have an optimization problem. The question is, can the answer be efficiently certified? So in all of these problems, or in any discrete optimization problem, if f of s, if this min over s is less than t, a certificate is given by that minimizer. Okay, so what am I saying here? So let me now describe a problem to you which you haven't seen. So what is the best way of doing this? Okay, let me discuss another problem. Let me discuss this problem that I call max cut. So you're given a graph. Okay, you have to break it up into two parts, so that the number of edges that go in between this part is, let's do min cut, is minimized. Okay, so this is some problem. I give you a graph, break it up, and you might have seen max cut, min cut before, but so you want to break it up into two parts, so that the number of edges going between that is minimized. Now, maybe you don't know how to do this. But if the min was less than t, could you be convinced of that in some way? And an easy way to convince you is someone actually gave you the cut that does this minimization. Does that make sense? So in all these optimization problems, computing the actual solution looks like it's difficult. But if you're given a particular solution, you can always check if it's less than t or not. That makes sense? Yeah?
So the certificate is S itself.
Is S, yes, exactly. The certificate is a solution. So what is, for shortest paths, the certificate is the path. If you wanted to convince me that the shortest path from U to V is less than something, then you could just give me that path to certify. If you wanted to prove to me that the length of the path is more than something, then it's not easy to certify. How would you certify that? You can give me a long path, but I could say maybe there's a shorter path. So there are some questions which are easy to certify and some questions that are not. Does that make sense? Like if I say, is this statement true, you can certify that by giving me a proof. But if I say, is this statement false, then how do you certify that? Does that make sense? So certification is a bit tricky. I mean, that's why a lot of questions here end up being related to cryptography, because this question about interacting with someone and certifying. So, and there are many questions of this form. There's min cut, there's like, well, I can define more and more, but that's not as important. The point is, for any discrete optimization problem, the question is min s f s less than t. This is the question we're studying. This is the main question. Determining the answer is not clear algorithmically. But if the answer is yes, certification can be done efficiently. Well, I said there exists. Okay, so what do I mean? I mean, finding this minimum might be hard. But if the answer is yes, there always exists a certificate that will convince you that the answer is true. Right? So, what is P? P means efficiently solvable, which are all the problems that we saw. We saw like MST, shortest paths, etc. NP is efficiently verifiable or certifiable. Which means that if the answer is true, there exists a certificate that can be checked efficiently. Okay, so there's P is essentially all the problems that you normally work with. These are problems where you know that you can actually solve it efficiently. I give you a problem and I say, give me a polynomial time algorithm. And you give a polynomial time algorithm, that means it's in P. Okay? But what NP means is something more it's something more general. It just says that I don't care whether I can solve the problem. If the answer is true, I just want to be able to verify it efficiently. Okay, that's what NP is. Sort of makes sense? So every discrete optimization problem is an NP. Why? Because if the min is less than t, there is a certificate, and that's exactly that S. And that S can be checked efficiently because f of s can be computed efficiently. There are questions that are not even an NP, that are much harder. Sort of making sense? So the P versus NP question says, if a problem is an NP, do we think it's in P? Like, just because a problem can be certified efficiently, do you think we can come up with a solution? This is just saying that checking a potential solution is efficient. And this is actually just saying that computing a solution is efficient. And the P versus NP question is, if a problem is efficiently certifiable, is it efficiently solvable? Indeed, we don't think that is the case. It seems that would be too much to be true. I'll give you an example of a problem where it's efficiently certifiable, but actually if you could efficiently solve this problem, you would break all modern cryptographic systems. Okay? And because we talked about long multiplication, I can just ask you, given a number, is it a product of two smaller factors? That's the question. Right? Given a number, is it a product of two smaller factors? Other than just one in itself, right? Yeah?
Well, I guess I just want to confirm P versus NP. So basically it's saying if you can efficiently check the solution, can you come up with an efficient solution?
Yes. No, can you come up with the most optimal solution? Not efficient, right? Yeah, this is like saying that. So the question is, so let me describe this question a little bit more formally. So I give you a number. It's the product of two numbers. Okay? But I just give you the product. And I say, can you compute the two numbers from which this was made a product? Right, this is the question. Okay? Now, to actually compute it would be like to factorize that number. But the NP version would just be like, if you show me the factors, then I can easily check that they're correct, just by multiplying and checking. So given a potential solution, I can check. You won't be able to fool me with a wrong solution. That's what NP means. And P means being able to come up with the solution. So if we could actually factor all numbers, then a lot of public key crypto systems will break. Because they're all based on the fact that we cannot factor numbers. So there's the secret actually happens to be these two numbers that are being multiplied together. That's like a cryptographic secret. And if you could break that, so this is based on the RSA system. If you've heard of the acronym RSA, then the RSA system is based on this. But there are many questions that have this flavor of checking a potential solution is quite efficient, but we don't know if computing a solution is efficient. So I'll give you one example. So does this sort of make sense? This is a distinction. And the P versus NP question is, if it's efficiently certifiable, do we think it's efficiently solvable? We don't think that is the case, but we don't have a proof. And the proof of this, essentially the entire field of cryptography is built on this assumption. It's built on even more assumptions. But this assumption is the basics. So let me give you an example of a question where it's not clear how to do. So this is a problem called clique, which I have worked on myself quite a bit. So what is the clique problem? I give you a graph. And this is a clique if, so this set S, if all pairs in S form an edge. Does this make sense? So a clique is like a set of vertices so that all pairs have an edge between them. Okay? And the problem is find the largest clique. Okay? So it's like I have a social network, and this comes up in social network analysis, where social scientists were studying this. It's like how big a group actually exists, where everybody is a friend of everybody else. What is the largest possible group? I give you a social network, I say find this. Okay? So in this problem, how do I certify a solution? If you gave me a clique, I can check the size. So is the largest clique more than T? That's easy to check, or easy to certify. Because if someone gave a solution, I can check, yes, this is a clique, and yes, it's more than a particular size. But how do I actually find the largest with that? Okay? So this problem, I'll give you the three-colorable problem. So you're given a graph. You need to break it up into three parts so that all the edges only go across in this way. Does such a partition exist. Does this make sense? I take a graph, I break it up into 3 parts, and all the edges have to go across these parts. Yeah?
What do you mean by all the edges have to go across these parts? Like, are those components all fully connected? Or?
These components, no, they're independent. They have no edge inside.
Oh, no edges inside only.
Yeah, so all edges across the partition.
So none of the nodes in those circles are connected?
None of these are connected by an edge. Interestingly, if you only had to break it up into 2 parts, this can be done with BFS. But to break it up into 3 parts, we don't know. I'll give you a problem that I asked in the midterm. Some version of that. Subset sum, right? Given numbers A0, A1, up to an minus 1, does a subset of them sum up to 0? It feels a lot like knapsack. Actually, knapsack is a classic problem. Like, it's just, I give you a bunch of numbers. Is there a subset of those that sum up to 0? Okay? That's another problem. So all of these problems you can see are in NP. Meaning, if there is a solution, and someone gave you the solution, there's an efficient piece of code that checks if the solution is correct. Right? Because in this case, it's easy to check. You can just check. All the edges go across. There's no edge in between. In this case, you can check if something is a clique. In this case, you can check. Okay, I give you a subset. It's easy to check that it's summing up to 0. The problem seems to be finding it. Yeah?
I mean, this is like just a question, a more general question. In practical applications, is this like, wouldn't the set of feasible answers be small enough that it's like reasonable to check all of them?
Not necessarily. Like which kind of, like if you look at clique, your social network is 1 billion vertices.
Oh, right, so you have to check them all.
So how do you know which is the right solution? In your typical situation like this, so it's a good question. So you say, why can't you just check all possibilities? The number of possibilities is exponential in the size. So it blows up really quickly. So for example, if you try to do all 3 partitions of a graph with even like 100 vertices, it's essentially infeasible. Do people want to color graphs with 100 vertices? Sure. Like the one place where graph coloring comes in is register allocation in a compiler. So what you do is you imagine this is all variables in your code. Okay? And I put an edge, means that these 2 variables occur in the same function or like same code block. What that means is I cannot put both those variables in one register because I need both of them at the same time. But if I have 2 variables that are in different code blocks, I can put them in the same register because I never need them at the same time. Does that make sense? And so graph coloring is like register allocation. Which are all the variables I can allocate to a register? Does that make sense? So it's essentially, and where you could imagine having a piece of code with like 1,000 variables. And if you wanted to find the best possible, this is related to, so this is like breaking it up into 3 parts. I can say, what is the minimum number of parts you need to break it into in terms of the allocation? Okay? So there's clique, there is 3 colorability. This is called subset sum. I'll give you another problem that you've probably seen, which is just n times n Sudoku. Okay, what is n times n Sudoku? It's just Sudoku with n cross n. Right? And I can ask, is there a solution? So this is Sudoku. So all of these problems, they are in NP. Because if I give you a solution, you can efficiently check that it's correct. But for all of these problems, we don't know of an efficient method to solve or optimize. Yeah?
So, like, what is the difference between, like, NP and, like, NP hard?
Good, I'm getting to that. So, NP hard are basically, okay, so good. So, that was the segue into the next part. So, or NP complete, if you've heard that phrase. So there are many problems that we have which are in NP, which are these discrete optimization, and no one's been able to find a solution, right? And so in the 50s and 60s and 70s, people sort of collected more and more of these problems, okay? And so at this point, with all this, I haven't really said much interesting stuff with P versus NP. This is where it gets interesting. What people ended up discovering is all of these problems, which look completely different, are really the same problem in disguise. They're really the same. There's like some underlying problem which is the same. And the theory of NP completeness tells you how to show that, and that's what it means to be NP hard. I'm lying a little bit, but that's basically the essence. So what that means is there actually happens to be a way of converting all these problems to each other, which is pretty crazy. It means that if you give me a clique problem, I can take it, I can convert it to an n-cross-n Sudoku, so that the clique problem has a large clique only if the Sudoku problem can be solved. And I can take the Sudoku problem and convert it to a subset sum, and convert that to a three-colorability or any which way, efficiently in polynomial time. So there's some caveats over there. So the point is, the theory of NP completeness gives a way of sort of trying to understand why there isn't an efficient